Good morning, all of you. So today we will learn binding fraction. So first of all, what is this binding fraction? Okay, what is this binding fraction? Binding fraction is nothing but average binding energy per nucleon. Binding energy per nucleon means delta m into c square value first you find out and just divide it by atomic mass number. Whatever value is coming, that is what your binding fraction, right? So let's write down first definition. What is the definition? The average binding energy the average binding energy per each nucleon is called binding fraction. Is called binding fraction. Okay. So if you want to write down formula, what is the formula? Simply binding fraction, that is BF, is equal to binding energy divided by A. That is equal to delta m c square divided by A, and therefore binding fraction is equal to delta m, and c square value we know how much, that is 931.5 mega electron volt by A. This is what your binding fraction value. We can keep it in a box. Now, what is the significance of this binding fraction? What is the significance? See, if binding energy per nucleon, that is binding fraction, is large, that nuclei is stable. If binding energy per nucleon is small, that nuclei is unstable. Got it? Let's write down that 2 points. First point, binding energy per nucleon is large, that is stable nuclei. If binding energy per nucleon is small, that is unstable nuclei. How it is? Large, that is stable nuclei, small, unstable nuclei. Got it? So note down this binding energy per nucleon, that is binding fraction. Note down fast. Yes, finished. Okay, next. Now next is binding energy curve. Binding energy curve. This binding energy curve is nothing but what? This is just a graph between binding energy per nucleon versus mass number. What is this? This is nothing but just a graph which plotted between binding energy per nucleon versus atomic mass number, as I said. Okay, so let's plot the graph. This is binding energy curve. This is 1. I'm taking like this point 1.6 and this is 8.79. This complete is what on y-axis, that is binding energy per nucleon in mega electron volt on this y-axis. Okay, and on this x-axis I am taking mass number. What I am taking? Mass number on this axis, like this. So this is 0, and let's plot the graph now. I'm just plotting the graph. You can also just wait for some time. like this. Here it is deuteron. Some elements I am writing. This is lithium. This one is carbon. Here it is calcium, and this one Fe. 8.79. Okay, some names I have given, and this one is there, no? This dotted one. This is the greater stability region. This region is what? Greater stability, or region of greater stability, we can say. Region of greater stability. That is, atomic mass number lies between 0 less than should be. Okay. This is what greater stability region. I will take this little this side. In the graph, so that you get idea about it should be around 40. Okay, so I am taking 50 here. Got it? This is what your binding energy curve. Now some points about this binding energy curve I am writing. Point number 1, minimum binding energy per nucleon. Minimum binding energy for per nucleon is for deuteron. Next point, just whatever you are observing from the graph, you have to see and write. It is maximum for ferrous. That is 8.7 mega electron volt, and this is most stable. This is most stable. Next point you can write about this graph. in the region of smaller mass numbers, in the region of smaller mass number, means this region, that is A is less than 30. The binding energy per nucleon shows characteristics minima and maxima. You can see here up and down are there. Next one, nuclei with A is greater than 170, means this region, are distinctly unstable, are distinctly unstable. And next point, light nuclei such as hydrogen combine to form heavy nucleus to form helium for greater stability. Helium for greater stability. Okay, so these are the some points which I have observed from this graph. And this graph is just nothing but binding energy per nucleon versus mass number. And why we have plotted this graph, so that we will get idea that which nuclei are more stable, which nuclei are not stable. Okay, like that. Just plot it and note down these points. Okay, let's move ahead. Next one is exoergic reaction. Is that exoergic? Exoergic means which releases energy. Exoergic reaction. So what is the definition of this reaction? When we can say any reaction is exorgic reaction, when it or when it emits energy. Reaction in which energy will be released. Next point, that is the reaction I am giving. A plus B gives C plus D plus some amount of energy, and where Q is equal to what? Delta M C square. Q is what? Delta M C square. And here these two are reactants, these two are products. Keep it in mind. So mass of reactant in these type of reactions, mass of reactant is greater than mass of product. Mass of product. Okay, mass of reactant means A and B mass is always greater than C and D mass. Okay, next one, this delta M is equal to mass of reactant minus mass of product, which is equal to mass of A plus mass of B minus mass of C plus mass of D. And therefore, what we are getting here, that is binding energy of products is greater than binding energy of reactants. Why? Because formula is what? Delta M C square. And whatever energy is getting released, that is Q, in these type of reactions. How to find that? So energy released, that is Q, is equal to binding energy of product minus binding energy of reactants. And therefore, if you want to find Q, Q is equal to binding energy of C plus binding energy of D minus binding energy of A plus binding energy of B. Okay, this formula you will use for finding the Q, that is energy released. Understand? Clear? Note down. Next. Now, endoergic reaction. What is next? Endoergic reaction. Now, exorgic reaction means what? Which releases energy. Now, here energy will be absorbed. Okay. In endoergic reaction, energy will be absorbed. So, see, first I am writing definition here also. The reaction in which the reaction in which energy will be absorbed is called endoergic reaction. is called Endoergic reaction. Got it? And see here, reaction same, A plus B will give C plus D. C plus D. But here Q is minus because energy is absorbed. That's why in this case you are getting like this. Now in this reaction, mass of reactant is less. Mass of reactant is less than mass of products. Mass of product. And here mass defect is equal to what? Increase in energy. Increase in mass. Okay, increase in mass, not energy, because some energy we have absorbed. No, that's why some mass will get increased. And here therefore delta m, that is mass defect, delta m is equal to mass of product minus mass of reactant, that is equal to mass of C plus mass of D minus mass of A plus mass of B. Okay, and here binding energy of products is less than binding energy of reactant. Binding energy of product is less than binding energy of reactant, in which Endoergic reaction, and therefore energy absorbed that is Q, capital Q is equal to binding energy of reactant minus binding energy of product, and therefore Q is equal to binding energy of A plus binding energy of B in bracket minus binding energy of C plus binding energy of D. This will give you the heat or energy absorbed during this Endorgic reaction, right? So you can see here difference. Here mass of reactants is greater than mass of products. Here mass of reactant is less than mass of product. Mass defect is increase in mass. Here mass defect is just subtraction. Here binding energy of product is greater. In this case binding energy of product is less. Here energy absorbed is reactant minus product. Here product minus reactant. Here C plus D and here A plus B. You can see here A plus B and C plus D. Got it? This is what your endoergic reaction. So on this, sometimes they are asking question to find Q value, right? So pause the video, note down this all notes carefully, and let's stop here for today.